In 1972, a 24-year-old graduate student named Jacob Bekenstein wrote down an idea the most famous physicist alive would soon call, in not quite these words, nonsense. He was quiet, stubborn, working at Princeton, and he had become convinced of something that sounded impossible, that a black hole, the one object in the universe defined by the fact that nothing escapes it, has a temperature, that it glows. Stephen Hawking set out to prove him wrong. Therefore, Hawking ran the calculation himself, certain it would bury the idea for good. It proved the kid right. What that one result cracked open has taken 50 years to face. It runs from a cup of tea cooling on a desk in 1970, through a single-page paper in Nature, through a bet settled with a baseball encyclopedia, to a wall of fire at the edge of a black hole and the cold death of the last star. By the end, the question is not whether the universe destroys what falls in. It is something worse. So get comfortable and subscribe or join if you have not. If you want the wider map, the deep time and the dead stars and the physics under all of it, that lives over on the Patreon. Stay to the end because it closes on the reason the universe keeps a perfect record of everything you are and makes certain no one can ever read it. Let's start where it started. The blackest object in the universe is glowing. Right now. Faintly, at a temperature so close to absolute zero that we have never measured it directly and almost certainly never will, but glowing, which is a word that should not be allowed anywhere near a black hole, because a black hole is the one object in all of physics defined entirely by the fact that nothing comes out of it. Not light, not matter, not heat, not a single bit of information about anything that ever went in. That is the whole idea. That is what the name was supposed to mean. And it is wrong. A black hole has a temperature. It radiates. It leaks. And that flat little sentence, the one I just said as if it were obvious, took the better part of a decade to be accepted. And it ended one of the strangest disputes in the history of modern physics. A dispute in which the most famous scientist of the 20th century looked at the work of a 24-year-old graduate student, a kid who had not even finished his doctorate, and told him, in not quite these words but close enough, that the idea was nonsense. Embarrassing, the kind of thing a serious physicist should be careful about putting his name to. And then that famous scientist went home, picked up a pencil, and did the math that was going to prove the kid wrong once and for all. He was certain it would. Everyone was certain it would. It proved the kid right. And here is the part I need you to hold on to, because it is going to sit underneath every single thing in this story, and it is going to get heavier every time we come back to it. If a black hole has a temperature, then it glows. If it glows, it loses energy. If it loses energy, it shrinks. And if it shrinks, then one day, after a stretch of time so long that the entire current age of the universe is a rounding error against it, the black hole is simply gone, evaporated, nothing where it used to be. Which forces a question that nobody in 1972 was prepared to ask out loud, and that physics is still fighting about today in real laboratories, on real chalkboards, in papers published in the last few years. When a black hole disappears, where does everything it swallowed go? Every star it ate, every planet, every cloud of gas the size of a solar system. And, in principle, every person, every book, every photograph, every last trace of everything that ever crossed that line. When the hole that ate them evaporates down to nothing, what happens to all of it? Does the universe keep a record of what was there? Or can the past, the actual past, be wiped so completely that not even the laws of physics remember it happened? That question is going to take us 2 hours and 45 minutes to fail to answer. I want to be honest about that up front. We are not going to solve it tonight, because nobody has solved it, and the people closest to solving it disagree sharply, in print, about whether it is even solved at all. But the failure is the most interesting thing I have read about in a long time, and the man at the centre of it died before he got to see how it turned out, and the man who fought hardest against it spent the last 40 years of his life losing to his own equations. So let me tell you about the cup of tea. It is 1970, an afternoon in Princeton, New Jersey, in an office in Jadwin Hall. And a physicist named John Archibald Wheeler is sitting across from his graduate student. Wheeler is one of those people who shows up at the edges of every important story in 20th century physics. He worked on the bomb. He coined the term black hole, or at least popularized it until it stuck. He taught Richard Feynman. He had a habit of asking questions that sounded almost childish, until you realized they were the deepest questions anyone in the room had thought to ask, and then he would chase them for 30 years. And on this particular afternoon he is bothered by something, and the something is a cup of tea. Here is the thing bothering him, in his own telling, which he wrote down years later. When you put a hot cup of tea next to a cold one and let them sit, the heat flows from the hot cup to the cold cup until they reach the same lukewarm temperature in between. Everyone knows this. It is the most ordinary thing in the world. But it is also, in the language of physics, a small crime. It increases the entropy of the universe. Entropy is the measure of disorder, of how many ways the pieces of a system can be arranged without you noticing the difference. And the iron law of thermodynamics, the second law, says that the total entropy of the universe can only ever go up, never down. When the 2 cups of tea even out, the universe has become a tiny bit more disordered, a tiny bit more shuffled, and that change can never be undone. The crime, as Wheeler put it, echoes down to the end of time. The universe keeps the receipt forever. And this genuinely troubled him. He said so. He said he felt like a criminal every time he let 2 cups of tea reach the same temperature, because he was nudging the entire cosmos a notch further toward disorder, and there was no taking it back. But then, Wheeler said, suppose a black hole happens to swim by, and suppose, instead of letting the teacups sit there incriminating me forever, I simply drop them both into the black hole. Now what? The cups are gone. The evidence is gone. The entropy I created, the disorder, the mess, all of it has vanished behind the event horizon where nothing can ever be seen again. I have concealed from all the world the evidence of my crime. The universe's books no longer balance, and nobody can prove they ever did. He meant it as a kind of joke, a thought experiment, the sort of thing a great physicist tosses out to a student to see what they do with it. The student took it home. His name was Jacob Bekenstein. He was born on the 1st of May, 1947, in Mexico City, to Polish Jewish parents who had gotten out of Europe before the worst of it. He became an American citizen in his early 20s. He studied at the Polytechnic Institute of Brooklyn, and then he came to Princeton to work under Wheeler, and by every account, he was quiet, careful, modest. The opposite of a self-promoter. A colleague who knew him for decades, Robert Wald, later said that Bekenstein was as tenacious as any physicist he ever met when it came to defending his ideas, but that he was never, ever a salesman. He did not push. He did not perform. He just thought, slowly and stubbornly, about whether things were true. You should understand how strange a thing it was, in 1972, to stake your career on black holes at all. The phrase black hole was barely a decade old. Wheeler had popularized it in 1967, and before that people called these objects collapsed stars or frozen stars or, in the original mathematics going back to Carl Schwarzschild in 1916, just singularities, and many serious physicists thought they were a mathematical artifact, a place where the equations broke down rather than a real thing that could exist in the sky. Einstein himself, whose own theory predicted them, spent years arguing they could not actually form. There was almost no observational evidence. The first strong candidate, an X-ray source called Cygnus X1, was only being confirmed around this very period, and Hawking himself had a famous bet with Thorne about whether it was real, a bet Hawking later conceded. So Bekenstein was not a young man playing with a well-understood toy. He was a young man insisting on the thermodynamic properties of objects that a good fraction of the profession was not sure existed, derived from a theory, general relativity, that most physicists at the time treated as an elegant backwater, far from the exciting frontier of particle physics, where the careers and the prizes were. He was an outsider working on the wrong topic, claiming the wrong thing, and he was about to be told so by the right people. And he could not let go of the cup of tea. To understand why, you have to understand what entropy actually is, because almost everyone is taught a version of it that is just wrong enough to hide the horror. You were probably told entropy is disorder, that a messy room has high entropy and a tidy room has low entropy, and that the universe tends toward mess. That is a children's version, and it leaks. The real definition, the one a physicist named Ludwig Boltzmann worked out in the 1870s, and that is so important it is carved on his gravestone in Vienna, is about counting. Entropy is a measure of how many different ways you can rearrange the invisible pieces of something, the individual atoms and their individual motions, while keeping everything you can actually see about it exactly the same. A cup of hot tea and a cup of cold tea are different in a way you can measure, but there are vastly, unimaginably more ways to arrange the trillions of molecules so that the tea is lukewarm than there are ways to arrange them so that half is scalding and half is freezing. Lukewarm is not disorder. Lukewarm is just overwhelmingly more likely, because there are overwhelmingly more arrangements that look that way. Entropy is the logarithm of that number of arrangements. It is a count of the universe's hidden options. And here is why that matters. Why Boltzmann's count is not bookkeeping, but the deepest thing anyone has ever said about time. The reason heat flows from hot to cold and never the reverse. The reason the tea cools and never spontaneously reheats. The reason a broken cup never reassembles itself off the floor. The reason you remember the past and not the future is entropy. The second law is not really a law about heat. It is the only law in all of physics that knows the difference between forward and backward in time. Every other fundamental equation we have, the ones governing particles and forces and fields, works exactly the same run in either direction. Play them backward and they break no rules. Only the second law, only entropy, only Boltzmann's count of hidden arrangements points an arrow and says, this way is the future. The increase of entropy is, as far as we can tell, the same thing as the passage of time. They may not be two facts, they may be one fact. So when Wheeler joked about dropping the teacups into a black hole to destroy the entropy he had created, he was not joking about a minor accounting trick. He was joking about reaching into the machinery of time itself and switching off the only thing in the universe that distinguishes the past from the future. If you could really destroy entropy, you could, in principle, make the universe forget which way time runs. That is the size of the thing Bekenstein could not let go of. Because the more he turned it over, the more it looked like the joke was actually a catastrophe. If you could destroy entropy by dropping it into a black hole, then the second law of thermodynamics, one of the most ironclad principles in all of science, the law that defines the direction of time itself, was not a law at all. It was a suggestion. It held everywhere in the universe except in the one place where you could cheat it, and once you can cheat a law of physics, it is finished. You do not get a second law that works most of the time. You either keep the receipts or you do not. So Bekenstein did the thing that almost nobody else was willing to do. He took the joke completely seriously, and he asked what the universe would have to be like for the joke to be false, for the crime to be impossible. And the answer he arrived at several months later, walking back into Wheeler's office, was so strange that his own advisor was not sure at first whether to believe it. "You do not destroy entropy when you drop the teacups into the black hole," Bekenstein said. "The black hole already has entropy, and by dropping the cups in, you only increase it." Sit with how odd that is. He was saying that a black hole, the simplest object you can imagine, an object so featureless that you can describe it completely with a tiny handful of numbers, is in fact one of the most disordered objects in existence. He was saying the black hole is keeping the receipt for you. The crime is not concealed. The black hole writes it down. Wheeler, to his enormous credit, did not laugh. He said, "Your idea is crazy enough that it might just be right." And that line, "crazy enough to be right," is the only thing that kept Bekenstein going through what came next, because what came next was years of nearly everyone in the field telling him he was wrong. Now, before we go further, I want to correct something, because the popular version of this story has been sanded down into a fairy tale, and you deserve the real one. You will hear it said that Stephen Hawking mocked Bekenstein, that he ridiculed him, that this is a simple tale of a cruel genius bullying a brilliant student. That is not quite what happened, and the truth is more interesting than the cartoon. What Hawking felt, by his own written admission, was irritation, and underneath the irritation was a genuine, serious, scientific objection that was very hard to answer. The objection was not snobbery, it was logic. And to understand it, you have to understand what Bekenstein was really claiming, because the claim was far more specific and far more dangerous than just black holes are messy. Here is what he actually wrote down. In 1972, he published a short note in an Italian physics journal called Lettere al Nuovo Cimento, and then in 1973 he published The Real Thing, the paper that would eventually rewrite physics, in Physical Review D, Volume 7, in the issue dated the 15th of April. The title was plain: Black Holes and Entropy. And the central claim of that paper was not just that black holes have entropy, it was a claim about exactly how much, and the answer was the most unexpected number imaginable. The entropy of a black hole, Bekenstein argued, is proportional to the area of its event horizon. You need to stop on that word. Area, not volume, not mass, not how much stuff fell in. The surface area of the invisible spherical boundary around the black hole, the point of no return, the place where the escape velocity hits the speed of light. The bigger that surface, the more entropy, the more hidden information, the more concealed disorder the black hole contains. And the relationship is precise. The information content of a black hole is written on its surface, and it scales with that surface. One bit of information for roughly every tiny square patch of the horizon. If your instinct is that this should depend on volume, you are in good company, because that is everyone's instinct, and it is wrong, and the wrongness of it is going to come back in about an hour and tear a hole in your understanding of what reality even is. For now, just file it away. The black hole keeps its books on its surface, not in its interior. Remember that. It is going to take on a meaning Bekenstein never intended. There was one number in his formula he could not pin down, a constant, a factor out front, something of about the size of 1, but he could not say exactly. He made an educated guess. He wrote that the constant was probably close to the natural logarithm of 2 divided by 8 pi, which is a perfectly reasonable thing for a physicist to estimate when the full machinery to calculate it does not yet exist. He flagged it as a guess. He knew it was the weak point, and that single unknown number is going to be the hinge the entire story turns on, because the man who finally calculated it exactly was the man trying to destroy the whole idea. But to see why Hawking and almost everyone else found this so hard to swallow, you have to understand what black holes were supposed to be in 1972, and you have to understand a result that had just landed and that everybody was very proud of. It was called, and I am not making this up, the no-hair theorem. The idea is this. In ordinary life, objects are complicated. A planet has mountains and oceans and weather. A star has flares and spots and churning convection. If you want to describe any normal object completely, you need an enormous amount of information. Every atom, every position, every velocity. But a black hole, the mathematics said, is different. Once matter collapses into a black hole and everything settles down, the resulting object can be described completely, with no information left over, by exactly 3 numbers: its mass, its electric charge, and its spin, how fast it is rotating. That is it. That is the entire object. 2 black holes with the same mass, charge, and spin are not similar. They are identical, indistinguishable in every possible way, even if one was made from collapsing stars and the other was made from collapsing encyclopedias and grand pianos and human beings. Physicists summarize this by saying a black hole has no hair, meaning no extra features, no individuality, nothing sticking out that would let you tell its history. The work was done by John Wheeler, by Werner Israel, by Brandon Carter, by Roy Kerr, by a whole constellation of brilliant people, and it was considered one of the cleanest, most beautiful results in the field. It was Wheeler, again, who gave it the name, and there is a story that the phrase "no hair raised eyebrows" when he first used it, that some of his French colleagues found the English wording faintly indecent, but it stuck because it captured something true and unnerving. A bald head looks the same from every angle. It carries no record of what was there before. And that is what the theorem says a black hole is: a perfectly bald object, smooth in a way nothing else in nature is smooth, betraying nothing about its past. Roy Kerr had found, in 1963, the exact mathematical description of a spinning black hole, and it was a thing of almost frightening economy. The entire object captured in a formula you could write on an index card. Werner Israel and Brandon Carter and others then proved the uniqueness, that any black hole, no matter how it formed, no matter the wild and specific history of the matter that collapsed to make it, settles down into one of these few clean shapes, indistinguishable from any other, with the same mass and charge and spin. It was beautiful precisely because it was so simple. A star is a riot of detail. A black hole is the erasure of detail, the universe taking something infinitely complicated and grinding it down to 3 numbers. And do you see the problem it creates? Do you see what it does to the cup of tea? Because if a black hole is completely described by 3 numbers, then everything else, every distinguishing feature of everything that ever fell in, is gone. Truly gone. You drop an encyclopedia into a black hole and a grand piano of exactly the same mass, and charge and spin into another, and the 2 black holes are now perfectly identical. The information about which was the encyclopedia and which was the piano has not been hidden. It has been erased. And if information can be erased, if you can take 2 different situations and funnel them into one identical outcome, then you have broken something far deeper than thermodynamics. You have broken the most basic promise physics makes about the universe, which is that, in principle. If you knew enough, you could always run the film backward. you could always reconstruct the past from the present. The no-hair theorem said no, you cannot, not if a black hole is involved. Bekenstein looked at the same theorem and drew the opposite conclusion. He said, the information cannot be gone, because if it were gone, the second law would be violated, and the second law is not negotiable. Therefore, the black hole must be storing it. Therefore, the black hole must have entropy. Therefore, and this is the line that made everyone uncomfortable, the black hole must have a temperature. Because entropy and temperature are joined at the hip, you cannot have one without the other. They are two faces of the same thing in thermodynamics, locked together by equations that have been tested for 150 years. If a black hole has entropy, it has a temperature, and a thing with a temperature above absolute zero does one thing always, without exception, everywhere in the universe. It radiates, it glows, it gives off heat, and that, right there, is the wall everyone slammed into. Because a black hole that radiates is a contradiction in terms. The defining property of a black hole, the thing that makes it a black hole and not just a very heavy star, is that nothing escapes it. Light goes in and does not come out. That is the whole point. So if Bekenstein was right that the black hole has a temperature, then it must radiate. But radiation is exactly the thing a black hole is forbidden from doing. The idea seemed to refute itself in a single step. It was, as far as the entire community could see, simply impossible. This is where Hawking comes in, and this is where it gets worse, because the way Hawking came in was to write a paper designed in part to put Bekenstein's idea in its place. And the irony of what that paper became is something I genuinely do not know how to fully absorb even now. In 1973, the same year Bekenstein's entropy paper came out, 3 physicists published a paper of their own. Their names were James Bardeen, Brandon Carter, and Stephen Hawking, and the paper appeared in a journal called Communications in Mathematical Physics, Volume 31. It was titled The 4 Laws of Black Hole Mechanics. And it was, in a way, a thing of beauty, because what these 3 had noticed was that the equations governing black holes had a structure that looked uncannily like the laws of thermodynamics. There were 4 parallels lined up one to one. The area of a black hole's horizon behaved exactly like entropy. It could only ever increase, never decrease, just as the second law demands. The surface gravity of the black hole, a measure of how fiercely it pulls at its own edge, behaved exactly like temperature, and it was constant all over the horizon, the way temperature is constant throughout an object in equilibrium. The matches went on, 4 of them, and they were not loose poetic resemblances. They were exact mathematical analogies. The equations had the same shape. Let me lay them side by side, because the precision is the thing that should bother you. Thermodynamics has a zeroth law, which says the temperature of an object in equilibrium is the same everywhere throughout it. Black hole mechanics has a matching law, which says the surface gravity is the same everywhere across the horizon of a settled black hole. Thermodynamics has a first law, the conservation of energy, which relates a change in energy to temperature times a change in entropy. Black hole mechanics has a matching first law, which relates a change in the black hole's mass to its surface gravity times a change in its horizon area, with the surface gravity sitting exactly where the temperature should sit, and the area sitting exactly where the entropy should sit. Thermodynamics has its famous second law: entropy never decreases. Hawking himself had proved, a couple of years earlier, the black hole area theorem, that the area of an event horizon can never decrease. That when black holes merge, the resulting horizon is always larger than the sum of the originals, exactly the behavior entropy shows. And thermodynamics has a third law, which says you can never actually reach absolute zero in a finite number of steps, and black hole mechanics has a matching law that you can never reduce the surface gravity to zero. Never make a black hole spin so fast or charge it so much that its surface gravity vanishes in a finite number of steps. 4 laws of heat. 4 laws of black holes, lined up one to one, the same mathematical structure in each pair, with area always standing in for entropy and surface gravity always standing in for temperature. This is not the kind of thing that happens by accident. When 2 completely different parts of physics turn out to obey equations of the same form, it is almost always because they are, underneath, the same physics. That is how progress usually works. Someone notices the equations match, and the match turns out to be telling you something real. And here is what Bardeen, Carter, and Hawking did with that astonishing fact. They said it was a coincidence, a formal analogy, a mathematical curiosity. They wrote explicitly that the resemblance was just that, a resemblance, and that the real physical temperature of a black hole was absolute zero. Zero. Nothing. Because of course it was zero. Because a black hole does not radiate. Because nothing comes out. Everybody knew that. The area looked like entropy, and the surface gravity looked like temperature, but you were not supposed to take it literally. It was a nice piece of bookkeeping. It was not real thermodynamics. I want you to feel how strange this is. 3 of the best physicists alive had found that the mathematics of black holes was, line for line, the mathematics of heat, and they looked at that, and they decided it had to be a coincidence, because the alternative, that it was real, led straight to the impossible conclusion that a black hole glows. They had the answer in their hands, and they set it down because it could not be true. Why did Hawking, in particular, want to set it down? He told us, decades later, with a candour I find almost unbearable. In his book A Brief History of Time, he wrote that part of his motivation in the 4 Laws paper was irritation with Bekenstein. He felt that Bekenstein had taken his own discovery, the discovery that a black hole's area always increases, and misused it, twisted it into this entropy business that Hawking thought was wrong. And then Hawking wrote the sentence that hangs over this entire story. He wrote that it turned out, in the end, that Bekenstein was basically correct, though in a manner Bekenstein had certainly not expected. Basically correct. Past tense. Written by the man who had set out to prove him wrong. But in 1973 that was still in the future. In 1973, Bekenstein was a young physicist holding an idea that the most powerful people in his field had just publicly labelled a coincidence, and he was mostly alone with it. He called them lonely years. Later, the encouragement from Wheeler, crazy enough to be right, was about all he had. Another colleague described the whole project of black hole thermodynamics, around that time, as foolhardy and highly unlikely to lead anywhere. Bekenstein himself said plainly, looking back, that Hawking had been a leader of the vociferous opposition, not a quiet skeptic, a leader of the opposition. And I want to be precise about what that opposition was, because it is easy to hear a story like this and reach for the word bullying, and that is not quite the shape of it. And the real shape is more useful. Nobody forged data. Nobody blocked his papers out of spite. The papers were published in good journals on time. What happened was subtler and in some ways harder to fight, which is that the most senior, most respected voices in the field simply treated the idea as not serious, and that judgment radiates outward through a discipline in 1,000 quiet ways. It shapes which talks get invited and which get scheduled against lunch. It shapes whether a young person can get a job working on the topic, whether a grant committee sees the area as promising or as a dead end, whether a graduate student is advised to stake their 20s on it or warned away. When the people at the top decide a question, is a curiosity rather than a frontier. The question does not get banned, it gets starved. And a starved idea, held by one stubborn young man with no institutional weight behind him, is one bad year away from disappearing entirely, not because it was refuted, but because everyone simply moved on. That is the mechanism, not a conspiracy. An ecosystem of incentives that quietly agrees what is worth a serious person's time. And that was, for several years, agreed that Bekenstein's idea was not. He survived it because he was, by temperament, almost immune to discouragement, and because one senior man, Wheeler, kept telling him the idea was crazy enough to be right. Take away that one mentor and the temperament, and the entropy of black holes might have sat in a drawer for another decade, waiting for someone less easily talked out of it. And he kept going anyway. In 1974, he published a second major paper, formalizing what he called the generalized second law of thermodynamics. The ordinary second law says the entropy of the universe never decreases. Bekenstein's generalized version said you have to add the black hole's entropy into the total, and then the sum. Ordinary entropy plus black hole entropy never decreases. Drop your teacups into the black hole, and yes, the ordinary entropy of the visible universe goes down, the mess disappears. But the black hole's entropy goes up by at least as much, because its surface area grows when it eats the cups. The books balance. The crime is recorded after all. The universe keeps its receipt, just in a place you can never look. It was elegant, it was consistent, it saved the second law, and it still required that black holes have a temperature and therefore radiate, which everyone still knew was impossible. So we have a standoff. We have a young man with a beautiful idea that cannot be true, and a famous man who has declared it a coincidence, and a wall of physical impossibility sitting between them that neither of them can get past. And the only way through that wall, it turns out, runs straight through the one piece of physics that Bardeen, Carter and Hawking had left out of their four laws entirely. They had written down the thermodynamics of black holes using nothing but Einstein's general relativity, the physics of gravity, of curved space and time. They had not used quantum mechanics at all. And the reason a black hole glows, the reason the impossible turns out to be true, lives entirely in the place where gravity and the quantum meet. Which, as we are about to see, is the single most dangerous neighborhood in all of physics. It is dangerous because it is where our two greatest theories stop agreeing with each other, and Hawking was about to walk into it carrying a calculation he was sure would end the argument. It ended the argument, just not the way he planned. The story of 1974 actually begins with Hawking trying to do something completely different. He was not setting out to confirm Bekenstein. He was, by his own account, still annoyed by the entropy idea and would have been delighted to bury it for good. What he was actually doing was a careful technical investigation of what happens to quantum fields near a black hole, and he was doing it, in part, because of two Russians he initially thought were wrong. In Moscow, a few years earlier, two physicists named Yakov Zeldovich and Alexei Starobinsky had argued, using quantum mechanics, that a rotating black hole should radiate, that it should slowly spin down by throwing off particles drawing on its rotational energy. Hawking visited Moscow in 1973 and heard this directly from them, and his reaction was, again, skepticism. He did not like their method. He thought the way they had done the calculation leaned on approximations he did not trust. So he went home to England to do it properly, to redo the calculation the right way, and, he assumed, to show that the effect was either smaller than the Russians claimed or absent altogether. That is the part that still amazes me. He set out to clean up what he saw as a sloppy result, and when he did the calculation carefully, it did not just confirm that rotating black holes radiate. It showed that all black holes radiate, spinning or not, that even a perfectly still, uncharged black hole, the simplest one imaginable, glows. The careful version gave a bigger, stranger, more universal effect than the version he had set out to correct. He went looking to shrink the radiation and instead found it was everywhere. So before we go further, you should sit with the pattern, because it is going to keep happening, and it is not a coincidence. Zeldovich and Starobinsky, dismissed, were pointing at something real. Bekenstein, dismissed, was pointing at something real. The dismissals were not stupid. They came from serious people with serious objections. But again and again in this story, the person being told they were wrong was the one standing closest to the truth, and the people doing the telling were defending a picture of black holes that was comfortable, established, and incomplete. Keep count of that. It matters more by the end. And to understand what he found, you need to understand one fact about empty space that almost nobody is taught, and that quietly dismantles the entire concept of nothing. Empty space is not empty. I mean this precisely, not poetically. According to quantum field theory, the most thoroughly tested framework in the history of science, accurate in some predictions to more decimal places than any other theory humans have ever written, the vacuum is not a void. It is a roiling, seething medium, full of fields that can never sit perfectly still, because the uncertainty principle forbids it. Everywhere, all the time, including in the room you are in right now. Pairs of particles flicker into existence and then annihilate each other and vanish again, too quickly to be caught directly, but with effects we have measured to staggering precision. These are sometimes called virtual particles. The vacuum is full of them. It is less like an empty stage and more like the surface of a boiling ocean seen from very far away, smooth from a distance, violent up close. Now, Hawking asked what happens to that boiling vacuum right at the edge of a black hole, right at the event horizon, where space and time are bent into shapes they never take anywhere else. And here I have to stop and correct something, because the explanation you have almost certainly heard for the answer is one that Hawking himself gave in his popular writing. And it is misleading, and physicists wince at it a little, even though they understand why he used it. The popular story goes like this. A pair of virtual particles pops into existence right at the horizon. One of them falls into the black hole, the other escapes, and the escaping one becomes real radiation, while the one that fell in carries negative energy and reduces the black hole's mass. It is a lovely picture, it fits on a napkin, and it is not really how the calculation works. The actual derivation is stranger and harder, and does not involve a clean little point on the horizon where a pair splits up. It involves the fact that the very definition of a particle, of what counts as empty space and what counts as a particle in it, depends on the observer. And an observer far from the black hole and an observer falling into it disagree, fundamentally, about whether the space between them is empty or full. The radiation comes out of that disagreement. It is woven into the geometry of the horizon itself, not produced at a spot on it. I tell you that not to be pedantic, but because it matters for the dread later. The radiation is not stuff leaking through a fence. It is the universe, near a black hole, being unable to agree with itself about what is even there. And if that sounds like a special pathology of black holes, here is the thing that should genuinely unsettle you, because it is not special to black holes at all. Around the same time, a physicist named William Unruh worked out that you do not even need a black hole to make empty space start glowing. You just need to accelerate. If you take a particle detector and move it through completely empty space, the deepest vacuum you can imagine, at a constant velocity, it detects nothing, as you would expect. But if you accelerate it, if you keep pushing it faster and faster, the detector starts clicking. it starts registering particles, a warm thermal bath of them, at a temperature proportional to how hard you are accelerating. The faster you accelerate, the hotter the empty space around you appears to be. This is called the Unruh effect, and it is a real prediction of the same physics, and what it tells you is staggering. Whether space is empty or full of warm radiation is not a fact about space. It is a fact about your motion through it. Two observers passing through the very same patch of vacuum, one drifting and one accelerating, will flatly disagree about whether there is anything there. One sees a perfect void, the other sees a furnace. And neither of them is wrong. A black hole, it turns out, is just a permanent gravitational version of that acceleration, because hovering near a black hole, resisting its pull, is physically identical to accelerating through empty space, by the very equivalence principle Einstein built his theory on. So the radiation Hawking found is the Unruh furnace, made permanent by gravity, paid for out of the black hole's own mass. The black hole glows for the same reason an accelerating detector clicks. Because the question of whether there is anything there does not have a single answer. Whatever picture you use, Hawking's calculation gave an answer, and the answer was the one thing he did not want. Black holes radiate. They emit a steady stream of particles, and the spectrum of that radiation is thermal, meaning it has exactly the statistical fingerprint of heat coming off a warm object, a glowing coal, a hot iron, the filament of a bulb. A black hole is not absolute zero, it has a temperature. The thing everyone knew was impossible was sitting right there in his own equations, and he could not make it leave. Listen to how he described it himself, a few years later. In an article in Scientific American, he wrote that like everyone else at the time, he had accepted the dictum that a black hole could not emit anything. He said he therefore put quite a lot of effort into trying to get rid of this embarrassing effect. And then, the line that I think about more than almost any other line in physics. It refused to go away, he wrote, so that in the end I had to accept it. He tried to get rid of it. It refused to go away. He had to accept it. There is a detail here that turns the whole thing from irony into something closer to tragedy, or maybe comedy depending on your mood. Hawking later admitted that part of what worried him, as the result refused to die, was Bekenstein. He wrote that he was afraid that if Bekenstein found out about the radiation, he would use it as a further argument to support his ideas about black hole entropy, ideas which Hawking, in his words, still did not like. Think about that. He had discovered the proof of the other man's theory, and his instinct, his very human instinct, was to worry that the other man would find out and be proven right. That is not a villain. That is a person. That is what it actually feels like to be wrong about something you have staked your reputation on in real time, while the evidence assembles itself under your own pencil. He published anyway. Because that is the job, and because he was, whatever else, a serious scientist. The paper came out in the journal Nature on the 1st of March, 1974, volume 248. And the title was a small masterpiece of understatement, with a question mark that did more work than any question mark in physics has ever done. The title was Black Hole Explosions, with a question mark, because if a black hole radiates, it loses mass, and as we will see, the smaller it gets, the hotter it burns, so the very end of a black hole's life is not a quiet fade, but a runaway, an acceleration, a final flash. Hawking had not just found that black holes glow, he had found that they die, and that they die violently. And the radiation has been called Hawking radiation ever since, which brings us to a moment that tells you everything about the character of the man who started all this. Because you might think Bekenstein, vindicated at last, would have fought to get his name on it. He did the opposite. When people asked, Bekenstein said plainly that the radiation should be called Hawking radiation, not Bekenstein radiation. I wrote it down first, he said, meaning the entropy, the temperature, the whole framework. But Hawking found the numerical value of the constant. The radiation was really Hawking's work. I had no idea how a black hole could radiate. Hawking brought that out very clearly. So that should be called Hawking radiation. The constant. Remember the constant. Remember the one number Bekenstein could not pin down, the factor out front of his entropy formula that he had to guess, the natural log of 2/8 pi, flagged as the weak point. Hawking's calculation pinned it down. Exactly, and the answer was beautifully, almost suspiciously, simple. The entropy of a black hole is exactly 1/4 of the area of its horizon, measured in the natural units of quantum gravity. 1/4. A clean fraction. The number Bekenstein could only estimate, the number that was the soft spot in his whole argument, turned out to be one of the most precise and famous numbers in theoretical physics, and it was delivered to him by the man who had been trying to prove he was wrong. The formula that came out of all this is now called the Bekenstein-Hawking entropy. Both names, fused, the skeptic and the student locked together forever in the same equation. It says that the entropy of a black hole equals its horizon area times the speed of light cubed times Boltzmann's constant, divided by 4 times the gravitational constant times Planck's reduced constant. You do not need to hold all of that. You need to hold the shape of it. Entropy equals 1/4 of the area, and the area is measured in Planck units, the smallest meaningful units of space. So what the formula is really saying is that a black hole stores 1 bit of information for roughly every 4 of the smallest possible squares of space you could draw on its surface. The information of everything inside written on the skin. Hawking, who had a sense of humour about these things, said he wanted that formula on his tombstone. When he died in 2018, his ashes were interred in Westminster Abbey between Isaac Newton and Charles Darwin, and the formula is engraved on the stone. The equation he spent years trying to prove was a coincidence is now carved above his remains, in a cathedral, between the 2 other men England buries its greatest scientists beside. But I have been throwing the word temperature around for a while now, and I owe you a number. Because the number is where the strangeness turns physical, and you can finally feel the scale of what we are talking about. How hot is a black hole, actually? The answer is that it depends entirely on the mass, and it depends in a way that is exactly backwards from your intuition. Big black holes are colder. Small black holes are hotter. The temperature is inversely proportional to the mass, which means the more a black hole eats, the more it cools down, and the smaller it shrinks, the more it heats up, which is the runaway that makes the ending an explosion. For a black hole with the mass of our Sun, the temperature works out to about 60 billionths of a degree above absolute zero. Let me say that more precisely. Around 60.1 billionths of 1 Kelvin. 60 nanokelvin. You cannot picture 60 billionths of a degree, so let me put it next to something. The coldest natural place in the universe, the deep space between galaxies, far from any star, is bathed in the leftover glow of the Big Bang, the cosmic microwave background, and that radiation has a temperature of about 2.7 degrees above absolute zero. A sun-mass black hole is something like 40 million times colder than the coldest empty space in the universe. It is so cold that it cannot possibly lose energy by radiating into the universe as it currently exists. Because the universe is warmer than the black hole, and heat flows from hot to cold, so a real black hole today is absorbing far more from the background than it emits. Every black hole astronomers have ever observed is, right now, getting bigger, not smaller. The evaporation, the glow, the death, all of it is real, but for the giant black holes that actually exist, it is being completely overwhelmed by the warmth of the cosmos around them. They will not begin to truly evaporate until the universe itself has cooled below their temperature, which will take a length of time we are going to confront later, and which is one of the bleakest numbers I have ever had to say out loud. This is, by the way, one of the great misconceptions I want to clear up while we are here, because it is everywhere. Hawking radiation is not something you could ever detect coming off the black hole at the centre of our galaxy or any other real black hole. Those objects are millions or billions of times the mass of the Sun, which makes them colder than 60 nanokelvin by a further enormous factor, down around 10,000ths of a trillionth of a degree, a temperature so absurdly low that the radiation is, for all practical purposes, indistinguishable from nothing at all. The supermassive black hole in the heart of the Milky Way is one of the coldest objects in the known universe. The glow we have spent the last half hour establishing is real, confirmed, carved on Hawking's tomb, and also so faint for any actual black hole that we will likely never measure it directly. It is a theoretical certainty and an observational ghost. That gap between what the math insists is true and what we can ever hope to see is going to matter enormously by the end. I want to make the coldness personal for a second, because there is a comparison here that I find genuinely difficult to hold in my head, and you should get to be unsettled by it too. Your body, right now, is about 300 degrees above absolute zero. A black hole with the mass of the Sun is 60 billionths of 1 degree above absolute zero. Which means you, the warm thing reading this, are something like 5 billion times hotter than the most extreme gravitational object physics describes. You radiate. You are glowing, in infrared, pouring heat into the room you are in. Far more fiercely and far more visibly than a stellar black hole ever could. The thing we imagine as the most violent, most powerful, most dangerous object in the universe is, thermally, almost perfectly dead, colder than anything you will ever touch, while you, a soft and temporary arrangement of water and carbon, burn against the cold of space like a tiny star. The black hole's power is not heat, it is patience. It will still be here, cold and nearly silent, 10 to the 67th power years after the last trace of your warmth has spread out into nothing. Hold that contrast. It is going to invert in the cruelest way when we reach the end, because the thing that outlasts everything is also the thing with the least left to say. While I am breaking misconceptions, here is another one, because it changes how you should picture all of this. A black hole is not a cosmic vacuum cleaner. It does not roam space sucking things in. If you replaced our Sun, right now, with a black hole of exactly the same mass, the Earth would not get pulled in. It would keep orbiting exactly as it does now, in the same ellipse, at the same speed, because from a distance the gravity of a black hole is identical to the gravity of any other object of the same mass. We would freeze in the dark, but we would not fall. Black holes only become deadly when you get close, closer than anything could orbit a normal star, into the region where the geometry of space itself tips over the edge. The danger is not appetite. The danger is geometry. And the geometry is what we have to go into next, because we have established that black holes glow and die, and now we have to face what that does to everything they ever swallowed. But before we can feel the weight of where the information goes, you have to accept one more thing that sounds like philosophy and is actually physics. Hard physics, with a number attached. Information is physical. It is not an abstraction floating above the world of atoms. It is part of the world of atoms, and it obeys thermodynamics, and erasing it costs something real. This took a long time to understand, and the story runs through a famous puzzle called Maxwell's Demon, dreamed up by the physicist James Clerk Maxwell back in 1867. Imagine a tiny intelligent being guarding a little door between two halves of a box of gas. Every time a fast molecule comes toward the door from the left, the demon opens it and lets the molecule through to the right. Every time a slow one comes from the right, the demon lets it through to the left. The demon does no work, just opens and closes a frictionless door, and yet, over time, all the fast hot molecules end up on one side and all the slow cold ones on the other. The box has sorted itself into hot and cold, for free. Entropy has gone down. The second law has been broken by a clever doorman. For nearly a century this puzzle sat there like a thorn, because nobody could quite say what was wrong with it. The answer, when it finally came, is one of the most beautiful and disturbing results in all of physics, and it ties information to heat with an iron chain. The demon, to do its sorting, has to know which molecules are fast and which are slow. It has to measure them, and remember the measurement, and act on it. And its memory is finite. Sooner or later, to keep working, it has to erase old measurements to make room for new ones. And in 1961, a physicist at IM named Rolf Landauer proved that erasing information is not free. Erasing a single bit of information, resetting one yes or no fact to a blank, must release a specific minimum amount of heat into the surroundings. An amount equal to a fundamental constant times the temperature. This is Landauer's principle. Forgetting has a thermodynamic price. The demon's sorting does lower the entropy of the gas, but the moment it erases its own memory to keep going, it dumps at least as much entropy back into the universe as heat. The books balance. The second law survives, and it survives specifically because information and entropy are, at bottom, the same currency. Hold that, because it changes everything that follows. Every bit of information in the universe is a physical thing with a thermodynamic cost. Your memories are physical. This sentence, sitting in your mind right now, is a particular arrangement of matter that the second law has its eye on. And when Bekenstein said a black hole has entropy, he was, whether he fully realized it in 1972 or not, saying that a black hole is the densest possible storehouse of information in the universe, the ultimate hard drive, the place where the most bits can be packed into the least space. Which means the question of what happens to information in a black hole is not a question about abstract data. It is a question about whether the universe is allowed to commit the one crime Landauer proved has a price. It is a question about whether forgetting, real forgetting, total forgetting, the kind where not even a trace of heat remembers, is possible at all. So let me say the thing plainly. The thing that all of this has been building toward, the thing that turned a beautiful result into a 50-year war. Hawking radiation is thermal. I said that earlier and let it pass, but it is the most important word in this entire story, so now we slow down on it. Thermal means random. It means the radiation coming off a black hole is featureless, structureless, carrying no information about what fell in, exactly the way the heat coming off a glowing coal carries no information about whether you burned an oak log or an encyclopedia to make it. The spectrum of Hawking radiation depends only on the black hole's mass, charge, and spin, those same three numbers. The no-hair numbers, nothing else. The radiation is, by Hawking's own calculation, the most boring possible signal, pure heat, pure noise. And now put the two halves of the story together and watch the floor open up. A black hole radiates thermally, which means the stuff coming out carries no information about what went in, and a black hole evaporates, which means that eventually all of its mass is gone, converted into that featureless thermal radiation, until there is nothing left. No black hole, no horizon, no interior, just an expanding cloud of random heat drifting off into space, identical whether the whole was built from stars or from libraries. So where did the information go? The encyclopedia fell in. The piano fell in. Every distinguishing feature of everything that ever crossed the horizon went inside. And then, over an unimaginable span of time, the entire black hole turned itself into structureless radiation that remembers none of it, and then the black hole itself disappeared. The information did not come back out, because the radiation that came out was thermal, random, blank, and the information cannot still be inside, because there is no longer an inside, there is no black hole anymore, the matter is gone, the horizon is gone. The information has, as far as this picture is concerned, been deleted from the universe. Not hidden, not scrambled, deleted, returned to nothing. If that sounds like a curiosity, a puzzle for specialists, I need you to understand why it is actually a 5-alarm fire at the foundation of physics. Because the deletion of information is not allowed. It is forbidden by quantum mechanics at the deepest level, more deeply than almost anything else the theory says. The principle is called unitarity, and it is the formal statement of the idea I mentioned much earlier, that you can always, in principle. Run the film backward. Quantum mechanics says that the present state of the universe contains, encoded within it, the complete information needed to reconstruct any past state. The universe never forgets. The information gets shuffled, scrambled, spread out, made practically impossible to read, but it is never ever destroyed. A pure quantum state evolves into another pure quantum state. It cannot turn into a blurry, information-poor thermal mess. That transformation, pure into thermal, is precisely the transformation that is not permitted. Let me make that concrete, because it is the hinge of the whole crisis. Think again about burning a book. When you burn an encyclopedia, it certainly looks like the information is gone. You are left with ash and smoke and heat, and you could never, in practice, read the book again. But a physicist will tell you, and mean it literally, that the information is not actually destroyed. It is in the ash and the smoke and the heat. Every photon of light from the flames, every molecule of smoke, every flake of ash carries away a tiny piece of the correlations that, if you could measure all of them with perfect precision and run the laws of physics backward, would let you reconstruct the original book page by page, word by word. It is hopeless in practice, requiring a measurement of every particle to infinite precision, but it is possible in principle, and in principle is exactly what unitarity protects. The burned book is a scrambled book, not a deleted one. The universe could, with godlike resources, read it. That distinction has a precise name in quantum mechanics. A state you have complete information about, even if that information is spread across 1 trillion particles, is called a pure state. A state where information has genuinely been lost, where the best you can do is give probabilities, is called a mixed state. And the central rule of quantum mechanics, the rule called unitarity, is that a pure state can only ever evolve into another pure state. It can become fantastically scrambled. It can never become genuinely mixed. The book can burn, but it cannot be deleted. Hawking's radiation does the forbidden thing. It takes the pure state of everything that fell into the black hole and turns it into thermal radiation, which is a mixed state, which is genuinely information poor, which really is deleted rather than merely scrambled. And you cannot escape it by saying, well, maybe the information got copied on the way in, copied onto the horizon as a backup before the original fell to the center. Because quantum mechanics forbids that too. There is a theorem called the no-cloning theorem that says you cannot make a perfect copy of an unknown quantum state. So you cannot have the information both fall in and stay outside as a backup. Either it is inside, doomed to be destroyed when the hole evaporates, or it is outside, in which case it never really fell in. The no-cloning theorem slams the easy exit shut. There is no backup. There is only the original, and the original is going into the furnace. And Hawking's calculation said it happens. Every time a black hole evaporates, it takes pure information and turns it into thermal radiation, the exact forbidden move. So now you have two of the most successful theories in the history of science. General relativity and quantum mechanics, the two pillars holding up all of modern physics, and they are no longer politely ignoring each other in their separate domains. They are standing in the same room, pointing at the same black hole, and calling each other liars. General relativity, through Hawking's own work, says the information is destroyed. Quantum mechanics says destruction is impossible. They cannot both be right. One of our two best theories of reality is wrong about something fundamental, and for 50 years nobody has been able to say which. This is the black hole information paradox. And the man who discovered it, the man whose own calculation created it, took a side. And the side he took was the one that should frighten you more. In 1976, Hawking published a paper with a title that sounds like the description of a nightmare, which in a sense it was. The title was Breakdown of Predictability in Gravitational Collapse, and it appeared in Physical Review D, Volume 14. In it, Hawking argued that the information is genuinely, truly lost, that the paradox is not a sign of a mistake in the calculation, but a discovery about how the universe actually works. He was saying, in effect, that quantum mechanics is the theory that has to bend, that when a black hole is involved, the universe really does forget, really does destroy the past, really does take pure states and grind them into thermal noise with no way back. He was willing to break the most sacred principle in quantum physics, rather than abandon what his black hole equations were telling him. And you have to respect the nerve of that, even as it disturbs you. Hawking had spent years not wanting black holes to radiate, and once they forced him to admit they did, he followed the consequence all the way to its bitter end, and was prepared to tell the entire physics community that one of its foundational beliefs was simply false. He had been wrong about Bekenstein, and rather than become cautious, he doubled down on being bold, just in the opposite direction. Most of his colleagues thought he was wrong again. Particularly the particle physicists, the people whose entire working lives were built on quantum field theory and its absolute conservation of information. To them, the idea that information could just vanish was as unthinkable as Bekenstein's glowing black hole had once been to Hawking. They were certain the information had to come out somehow, that the thermal appearance of the radiation was a limitation of Hawking's approximation, that a deeper theory would show the information sneaking out encoded in subtle correlations between the particles. The way a clever enough analysis of smoke and ash could in principle reconstruct the book you burned. So the lines were drawn, and the war settled in for the long haul, and it lasted decades, and at one point it became, of all things, a bet. I love this bet, because it shows you that physicists, when they are deadlocked, do exactly what anyone else does, which is to put money on it. In 1997, on the 6th of February, 3 physicists signed a formal wager. On one side, Stephen Hawking and Kip Thorne, the great relativist, both betting that information really is destroyed in a black hole, that Hawking's 1976 position was correct. On the other side, a quantum theorist named John Preskill, betting that the information escapes, that quantum mechanics survives, that the universe keeps its receipts after all. They wrote it up properly, signed it, the whole thing, and the stakes, the wager, was an encyclopedia. The loser would buy the winner an encyclopedia of the winner's choosing, from which, the bet noted with a certain dark wit, information can always be freely retrieved. That was the joke. An encyclopedia is the perfect object to bet on a paradox about information, because the entire question is whether the universe is like an encyclopedia, something you can always read the truth out of, or like a fire, something that turns the book into heat and forgets it forever. These were not minor figures making a cute wager. Kip Thorne would go on, 20 years later, to win the Nobel Prize in Physics for his work on detecting gravitational waves, the ripples in space-time that Einstein predicted and that humanity finally caught in 2015. John Preskill would become one of the founding figures of quantum computing, the field now staking billions on the very principle at the heart of the bet. That quantum information is precious and conserved and never truly lost. And Hawking was Hawking, the most famous scientist on the planet, a man who by this point spoke through a computer, one carefully chosen word at a time, because the disease that had been given 2 years to kill him in 1963 had instead left him almost completely paralyzed across 4 decades, while his mind kept working at full speed. 3 of the most serious people in physics, signing a piece of paper about whether the universe remembers its past, and choosing as their stake the most mundane possible symbol of retrievable knowledge, a reference book. They understood exactly how strange it was to be betting on this. That was the point of the joke. The joke was a way of admitting that grown adults at the top of their field genuinely did not know whether the past can be erased, and had no way to find out except to argue for decades and see who broke first. And here is where I have to plant something, because we are about halfway into this story, and the deepest part of it is starting to take shape under everything else. And I want you to feel it arriving before it fully lands. The information paradox looks like a technical quarrel about black holes. It is not. It is a quarrel about whether the past is permanent. Whether the universe is the kind of thing that keeps a complete and perfect record of everything that has ever happened, every event, every arrangement of matter, every moment of every life, preserved somewhere in the present state of reality even if no one can read it, or whether the past can be truly finally erased, dropped into a furnace that does not just hide it, but unmakes it, so that not even the laws of physics retain any trace that it was ever there. That is what Hawking and Preskill were actually betting on, not the fate of some encyclopedia, the fate of memory itself at the level of the cosmos. Whether anything that happens, including everything you have ever done, is written down somewhere forever, or whether it can be unwritten. Hold that, we are going to come back to it, and when we do, the answer is going to be worse than either side of the bet imagined. The bet sat there, unresolved, for 7 years, and then, in 2004, something happened that made headlines around the world, and that is usually told as the happy ending of this story, and that is not the ending at all, because the story does not have an ending, but it is the moment the public was told the puzzle had been solved. In July of 2004, at a major physics conference in Dublin, the 17th International Conference on General Relativity and Gravitation, Stephen Hawking asked for time to speak. He had a new result, and in front of the world's press, he conceded the bet. He announced that he had changed his mind, that he now believed the information does, after all, come back out of the black hole, that quantum mechanics wins, and unitarity holds, and the universe keeps its receipts. He had been wrong, he said, for nearly 30 years. He paid Preskill the encyclopedia, and in keeping with the spirit of the joke, he chose a baseball encyclopedia, a doorstop of a thing called Total Baseball, the ultimate baseball encyclopedia, from which, as he noted to the laughing audience, information can indeed be freely retrieved. He added that he probably should have just given Preskill the ashes, since burning the book and handing over the ashes would have been the more appropriate gesture, except that it would have been very hard for Preskill to read. The press loved it. Hawking changes his mind. Hawking solves his own paradox. Information escapes black holes after all. Mystery solved. You probably absorbed some version of this somewhere at some point as a settled fact. Black holes do not destroy information. Hawking admitted he was wrong. Done, and this is the place to say something plainly, because it is the quiet engine under this whole story, and it explains why you were handed a fairy tale instead of the truth. The public does not get the version of science that is true. The public gets the version that is tellable. A famous man stood up at a conference and conceded a bet about black holes, and that is a story with a beginning, a middle, and an end. A story with a punchline and a baseball encyclopedia. A story you can put in a headline and a textbook sidebar and a documentary voiceover. The actual situation, which was that one of the bet's other participants refused to concede, that the conceded argument contained no working mechanism, that the deepest contradiction in physics remained wide open and would within a decade get dramatically worse, is not a tellable story. It has no punchline. It does not end. So, it did not get told, not because anyone lied, not because of a conspiracy, but because institutions, including the institution of science journalism and the institution of physics itself managing its public image, reach for closure the way water reaches for the lowest point. A solved mystery is fundable, quotable, teachable. An open wound is just uncomfortable. And so the most honest description of where things actually stood, which was that nobody knew, got quietly replaced in the public mind by a tidy obituary for a paradox that was very much still alive. You were told the case was closed because the closed version was easier to carry. Keep that in mind for the rest of this, because the same thing is about to happen again in 2020, with even better headlines. It was not done. It was not close to done. And the proof that it was not done is that Kip Thorne, who had been on Hawking's side of the bet, refused to concede. He was not convinced. He looked at the same argument Hawking had made, the argument that supposedly resolved the paradox, and he said, in effect, I am not satisfied. The case is not closed. I am keeping my position. One of the two losers of the bet did not think the bet had actually been settled, and he was right not to, because Hawking's 2004 argument, based on a technical idea about summing over different space-time geometries, did not actually show in any detail anyone could fully reconstruct how the information gets out. It gestured at a resolution. It did not deliver a mechanism. It was a brilliant physicist's intuition that the answer must be unitarity, dressed in enough mathematics to concede a bet, but it did not silence the people who wanted to see the information actually escape, step by step. So the paradox did not die in Dublin. It went quiet for a few years the way these things do, and then in 2012 it came back. And when it came back it was angrier than ever, and it had a new name, and the new name was a warning. The new name was Firewalls. But to feel why the firewall was such a shock, you have to know what physicists thought they had already settled, the truce they had been quietly living under for almost 20 years. Back in the early 1990s, before Dublin, a few people, chief among them Leonard Susskind and Gerard 't Hooft, had proposed a way to have it both ways, a way to keep the information escaping without ever catching the universe in a contradiction. They called it black hole complementarity, and it is one of the slipperiest, most quietly terrifying ideas in physics, because it does not resolve the paradox so much as declare that the paradox can never be observed, and then dares you to say that is not good enough. Here is the idea. To an observer who stays safely outside the black hole, the infalling matter never actually crosses the horizon. It appears to slow down, redden, and smear out across the surface, its information getting cooked into the horizon and eventually radiated back out in the Hawking radiation. Information preserved, no problem. But to an observer who falls in with the matter, nothing special happens at the horizon at all. They sail straight through, no drama, and find the information happily inside with them. So which is it? Is the information smeared on the surface, or is it inside? Complementarity's answer is a kind of shrug that should make your skin crawl. It is both, and you are forbidden from ever proving the contradiction, because no single observer can ever be in both places. The one who stays outside can never see inside. The one who falls in can never get back out to compare notes. The two stories contradict each other flatly, and the universe is arranged so that no one, anywhere, can ever stand in a position to catch the contradiction. It is not that there is no contradiction, it is that the contradiction is hidden behind a horizon, perfectly, forever, and physics simply asks you to be satisfied with that. For almost 20 years, people were more or less satisfied with that. It felt like a cheat, but it was a cheat you could not disprove, and in physics a paradox you can prove will never bite you is close enough to a solution that everyone exhales. That exhale is what amps interrupted. Because they found a way on paper to catch the contradiction after all. To understand the firewall, you have to understand a beautiful idea that everyone had been leaning on to make the paradox feel survivable, and then you have to watch 4 physicists tear that idea apart with nothing but careful logic. The beautiful idea is the equivalence principle, and it is the deepest thing Einstein ever discovered. The seed of general relativity itself. It says that falling freely under gravity feels like nothing at all. If you are in free fall, you feel weightless, you feel fine, you cannot even tell, locally, that there is any gravity acting on you. An astronaut in orbit is in free fall and floats serenely. And the principle extends to black holes in a way that is genuinely surprising and that physicists had come to accept. If you fall into a large enough black hole, the equivalence principle says that crossing the event horizon, the point of no return, should be a complete non-event. Nothing special happens there. There is no wall, no surface, no marker. You would sail across the horizon of a supermassive black hole without noticing a thing. No jolt, no heat. No sign that you had just passed the boundary beyond which you can never return. The horizon, in this picture, is not a place. It is just the last point from which light can still escape, and locally, to you, falling, it is as empty and unremarkable as any other patch of space. Physicists call this no drama. Crossing the horizon is supposed to be drama-free. In 2012, 4 physicists at the University of California, working at Santa Barbara and Stanford, named Ahmed Almheri, Donald Marolf, Joseph Polchinski and James Sully, known forever after by the first letters of their names as amps, published a paper that proved you cannot have everything. They showed, with a chain of reasoning that is almost impossible to escape, that 3 things physicists desperately wanted to all be true cannot all be true at once. You can have unitarity, the survival of information, quantum mechanics intact. You can have the validity of ordinary physics outside the black hole. And you can have no drama at the horizon, the smooth, empty crossing that Einstein's equivalence principle demands. You can have any 2. You cannot have all 3. The math simply does not permit it, and the conclusion they drew, the one that gave the paper its terrible name, was this. If you insist on keeping unitarity, if you insist that the information escapes and quantum mechanics is saved, then you have to give up no drama. You have to accept that the horizon of an old black hole is not a smooth, empty, unremarkable place. It is a wall of lethal energy. A firewall. An infalling astronaut would not sail gently across the horizon noticing nothing. They would hit a sheet of radiation at very nearly the speed of light and be incinerated instantly, burned to their most basic particles, at the very boundary that Einstein's greatest principle insisted should feel like nothing at all. Think about what that means as a choice. To save the idea that the universe keeps its records, you have to destroy the idea that free fall feels like nothing, the single most beautiful and well-tested foundation of our theory of gravity. To save Einstein's equivalence principle, you have to accept that information really is destroyed and quantum mechanics really does break. Every road leads off a cliff. Amps had taken the information paradox, which was already a contradiction between two theories, and sharpened it into a contradiction you could feel on your own skin. A choice between being lied to about the nature of memory or being burned alive at a boundary that should be empty. The field went into something close to crisis. Polchinski, one of the four, was one of the most respected theorists alive, not a provocateur, and when he and his colleagues said the emperor had no clothes, people could not just wave it away. Leonard Susskind, who we are about to meet properly because he is central to everything that follows, called the Firewall argument the most surprising and disturbing development in the subject in years. There were conferences. There were furious papers. There were brilliant people publicly admitting they did not know which of their most cherished beliefs to give up. The abdication was total. The people who were supposed to understand black holes better than anyone on Earth were standing in front of a chalkboard, openly conceding that their best theories, taken together, predicted an impossibility, and that they had no idea how to fix it. I want to stay with Joseph Polchinski for a moment, because there is an ironic parallel in his story that I have not been able to shake. Polchinski was one of the towering figures of late 20th century physics, the man who had discovered the objects called D-branes that reshaped string theory in the 1990s. The author of the textbooks a generation of theorists learned from. The firewall was one of the last great problems he threw himself at, and a few years after the firewall paper, Polchinski was diagnosed with brain cancer. He underwent the surgeries and the radiation, and he wrote with remarkable openness a memoir of his life in physics that he finished while undergoing treatment, knowing what was coming. The treatments that kept him alive also damaged his memory, took pieces of his recall, blurred the very faculty a theoretical physicist lives by. Here was a man who had spent his final healthy years arguing about whether information can be destroyed at the edge of a black hole, about whether the universe is permitted to forget, and he spent his final years watching his own mind, the most precise instrument he owned, slowly lose its grip on what it had known. He died in 2018, the same year as Hawking. The man who proved the universe faces an impossible choice about whether to preserve information was himself, at the end, losing his. I do not raise that to be morbid. I raise it because this entire story is underneath the equations about that exact fear, the fear of erasure, scaled up from one human mind to the whole of reality, and the people doing the physics were never separate from the fear. They were living inside it. And the resolution, when it finally started to come, did not come from black holes at all. It came from an idea that sounds, at first, completely insane, an idea that grew directly out of Bekenstein's 1973 observation, the one I told you to remember, the one about area instead of volume. Because the answer to where the information goes turned out to require throwing out something so basic that you have never once questioned it in your life. It required throwing out the idea that the world has the number of dimensions it appears to have. Let me bring in Leonard Susskind properly, because he is the one who chased this furthest, and because the way he tells it is the way I want you to feel it. Susskind is a physicist from the South Bronx, the son of a plumber, who came into physics from the working class and never lost a certain bluntness about it. He was one of the founders of string theory. He spent years in a running intellectual battle with Hawking over exactly this question, a battle he affectionately and accurately called the Black Hole War, and he wrote a book by that name, and in it he is absolutely clear that the war was scientific, never personal, that he and Hawking liked and respected each other enormously even as Susskind became convinced that Hawking's information loss position was, in his words, dead wrong and dangerous. Dangerous because if Hawking were right, it would bring down the whole edifice of physics. And the weapon Susskind eventually reached for came from Bekenstein's area law. Here is the chain of reasoning, and it is one of the most vertiginous chains in all of science, so we are going to take it slowly. Bekenstein said the entropy of a black hole, the amount of information it can hold, is proportional to its surface area, not its volume. Now push on that. A black hole is the densest possible way to pack mass into a region of space. You cannot cram more stuff into a given volume than a black hole already does, because if you try, you just make a bigger black hole. Which means the black hole's entropy, its information content, is the maximum possible information content for that region of space. Anything you put in that region holds less information than the black hole would. The black hole is the upper limit, and the black hole's information scales with area, not volume. Therefore, the maximum amount of information that can possibly be contained in any region of space is set by the area of the surface surrounding that region, not by the volume inside it. Stop and feel how wrong that is. Your intuition screams that a bigger box holds more stuff than a smaller box, because it has more room inside. More volume. But this result, which is a rigorous consequence of black hole physics, and is called the Bekenstein bound, says no. The amount of information you can fit in a region is fixed by the size of its boundary, the wall around it, the two-dimensional surface, not by the three-dimensional space it encloses. It is as if the universe only has room to write things on surfaces, and the interior is, in some sense, along for the ride. Let me put numbers on this, because the numbers are where it stops being abstract and starts pressing on your own body. The Bekenstein bound gives you the maximum amount of information that can be packed into any region, and you can run it for things you know. A human being, all of you, every atom and every quantum state of every atom, can be fully specified by something on the order of 10 to the 45th power bits of information. That is the absolute ceiling, the most that could ever be said about you, the size of the file the universe would need to reconstruct you exactly. A region the size of a human brain caps out around 10 to the 42nd power bits, and the entire observable universe, everything we could ever see, all of it, has an information ceiling of around 10 to the 120th power bits. These are finite numbers, large beyond comprehension, but finite. There is a largest possible amount of you. There is a largest possible amount of everything. And the bound also tells you something about the texture of reality at the smallest scale, which is that reality appears to be, in a sense, pixelated. The information lives on the surface at a density of about 1 bit for every 4 units of Planck area, and a Planck area is unthinkably small, about 10 to the negative 70th of a square meter, a square whose side is the Planck length. The scale below which the very concepts of distance and area may stop meaning anything. So the surface of any region is not a smooth continuous sheet. It is, if the holographic principle is right, more like a screen made of the smallest possible pixels, each one holding a single bit, and the three-dimensional world inside is the image those pixels are displaying. The smoothness of space, the seamless continuity you feel when you wave your hand through the air, may be exactly like the smoothness of a photograph on a high-resolution screen, an illusion produced by pixels too small to see. In 1993, a physicist named Gerard 't Hooft, one of the sharpest minds in the field, took this to its logical and outrageous conclusion in a paper about dimensional reduction in quantum gravity. And in 1995, Susskind sharpened it into a specific, almost unbelievable proposal, published in the Journal of Mathematical Physics, Volume 36, under a title that tells you exactly how far he was willing to go. The title was The World as a Hologram. Here is the claim. If all the information in any region of space can be encoded on the boundary of that region, then maybe the three-dimensional world we live in, the world of depth and volume and distance, the world where you can walk across a room, is not fundamental at all. Maybe it is a kind of projection. Maybe the real description of reality, the place where the actual information lives, is a two-dimensional surface, some distant boundary, and everything we experience as three-dimensional space, including the very feeling of depth, is encoded on that flat surface, the way a hologram encodes a three-dimensional image on a flat piece of film. Susskind wrote, following Hooft, that the combination of quantum mechanics and gravity requires the three-dimensional world to be an image of data stored on a two-dimensional projection. He put it even more starkly in his popular writing. The three-dimensional world of ordinary experience, he wrote, the universe filled with galaxies and stars and planets and houses, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. I want to be very careful here, because this is exactly the kind of place where physics gets twisted into mysticism by people who want it to mean something it does not. This is not a claim that the world is fake, or that we are in a simulation, or any of that. It is a precise mathematical claim about the equivalence of two descriptions. It says there is a description of our universe written on a lower dimensional boundary that contains exactly the same information as the full higher dimensional interior, no more and no less, and that the two are, in a deep sense, the same physics seen two ways. But the precision does not make it less unsettling. It makes it more unsettling, because the mathematics is not vague about this. In 1997, a young Argentine physicist named Juan Maldacena wrote down an actual, concrete, calculable example of it, a specific case where a theory of gravity in a five-dimensional space is provably exactly equivalent to a theory without gravity living on the four-dimensional boundary of that space. The interior with its gravity and its extra dimension, and the flat boundary without them, are the same theory. Maldacena's paper became the most cited paper in the history of theoretical physics. Tens of thousands of physicists have built their careers on it. It is not fringe, it is the mainstream. It is, in the corner of the field where these questions live, the closest thing there is to consensus. And what it says, stripped of the jargon, is that the dimensionality of your world, the number of directions you think you can move in, may not be a fundamental fact about reality. It may be an artifact of how the information is displayed. I should tell you what kind of universe Maldacena actually solved this in, because the detail matters, and it is going to come back to haunt the happy ending. He did not solve it for our universe. He solved it for a universe in a box. The technical name is anti-de Sitter space, and the thing you need to know about it is that it has a boundary, a wall at the edge of infinity, a place where the universe ends and you can write things down. Our universe does not seem to have one of those. Ours expands openly, with no edge to pin a description to. But anti-de Sitter space curves back on itself in a way that gives it a boundary you can hold, like the inside of a snow globe, and on the surface of that snow globe lives an ordinary quantum theory with no gravity in it at all, no curved space, no black holes, nothing falling. And Maldacena proved that the flat, gravity-free theory painted on the glass and the rich three-dimensional gravity-filled world sloshing around inside the globe are not two universes that resemble each other. They are the same universe, written in two languages. Every black hole that forms inside the globe corresponds to a blob of hot particles on the surface. Every detail of the gravitational interior is somewhere in the boundary description, fully, exactly, with nothing left over. This is the single most important theoretical idea in physics in the last 30 years, and it is worth sitting with how strange it is that it works. Gravity, the force that built every star and bent every ray of light, and holds you to the floor right now can be made to completely disappear, traded away for an ordinary quantum theory on a distant surface with one fewer dimension. Gravity in this picture is not fundamental. It is what the boundary information looks like when you let it organize itself into a world with depth. The pull you feel is the texture of a hologram, and because the boundary theory obeys ordinary quantum mechanics, where information is never destroyed, the interior must obey it too, which means a black hole inside the globe cannot destroy information, because its description on the boundary certainly does not. That was the first real reason to believe Hawking had to be wrong about information loss. Not a calculation about the black hole itself, but a mirror held up to it from the edge of the universe, showing a reflection that obviously kept its receipts. And here is the part that closes the loop and made the firewall start to dissolve. If the information about the inside of a black hole is really encoded on its two-dimensional horizon, the way the hologram principle says, then the question where does the information go has a strange new answer. It was never only inside. It was in a sense always also on the surface, written on the horizon, and the radiation coming off the horizon could carry it away after all, not as a violation of anything, but as the natural reading out of information that was stored on the boundary the entire time. The black hole interior and the black hole horizon are not two separate places fighting over who has the information. They are, like Maldacina's interior and boundary, two descriptions of the same thing. The encyclopedia that fell in and the radiation that comes out are not connected by some impossible signal escaping from inside. They are the same information, described twice. If your head is spinning, good, mine still does. Because what we have just done is answer the question, where does the information go, by dismantling the meaning of the word where. The information is not in the interior or on the surface, because interior and surface are the same thing seen from two angles, and the deeper you push, the more it seems that the comfortable three-dimensional space you live in, the space where things have definite locations and you can point at where something is not the bedrock of reality, but a high-level description floating on top of something else, something flatter and stranger, and written in a language of pure information that does not care about depth at all. That should disturb you more than the firewall did. The firewall threatened to burn an astronaut. The holographic principle threatens the idea that the astronaut was ever really located anywhere in 3 dimensions in the first place. And yet, even the dissolution of dimensionality itself, was not the resolution. It was a clue. The actual resolution, the one that has people very cautiously using the word solved in the last few years, did not arrive until 2019 and 2020. And it is the most recent chapter of this story, and it is genuinely beautiful, and it is also, I have to keep insisting, not as finished as the headlines made it sound. So let me tell you what actually happened, and what it actually means, and where the dread that has been building under all of this finally surfaces and refuses to go back down. To understand the breakthrough, you have to understand what a correct answer to the paradox would even look like, and for that you have to meet one more idea, which is called the Page curve, named after a physicist named Don Page, who was, in one of those details that makes this whole history feel almost too neat, a former graduate student of Stephen Hawking's. Page asked a sharp question back in the 1990s. Forget the details of the mechanism. Just ask, if information really does escape a black hole, what should the radiation look like over time? Not the energy, the information, the entanglement. He worked out that if quantum mechanics holds, if information is preserved, then the amount of information carried by the radiation should follow a very specific shape over the black hole's lifetime. Early on, as the black hole begins to evaporate, the radiation should look thermal, look random, look information-free, exactly as Hawking calculated. But there should come a moment, roughly halfway through the black hole's life, now called the page time, when the trend reverses and the radiation should start carrying information back out. The entanglement should start to decrease until by the time the black hole has fully evaporated, all the information has come out and the books balance. That reversal, that turnaround plotted on a graph, is the page curve. If you can show by honest calculation that the radiation follows the page curve, you have shown the information escapes. If your calculation gives Hawking's original answer, the entanglement just rising forever and information lost, you have not. For decades, every honest calculation gave Hawking's answer. The information looked lost. Nobody could derive the page curve from the actual physics of an evaporating black hole. Susskind could argue for it. Maldaceno's correspondence suggested it had to be true, but nobody could turn the crank and watch the curve bend. Then, in 2019, working independently and then together, several groups of physicists, including Jeff Pennington and Ahmed Almheri, the same Almheri from the Firewall paper, and Netta Engelhardt and Don Marolf and others, found a way to do the calculation honestly, using the tools of the holographic principle, and the curve bent. The entanglement rose, reached the page time, and turned over and came back down, exactly as Page had predicted 30 years earlier. The information comes out. They could finally show it in the mathematics, with a real calculation rather than an intuition. The way they did it is one of the strangest things I have ever read in a physics paper, and I want to give it to you straight, even though it sounds like science fiction. The calculation works when you include contributions to the black hole's geometry from things called replica wormholes, configurations in which the interior of the black hole is secretly connected, through the mathematics of the gravitational path integral, to the radiation that has already escaped, and to copies of itself. And there emerges a region deep inside the black hole, near the center, which the calculations call the island, and the island, against all intuition, turns out to belong to the radiation outside. The information in the island is encoded in the distant radiation. The interior of the black hole, its deepest part, is somehow part of the same system as the radiation that left long ago, connected across the apparent emptiness by the geometry of space-time folding back on itself in ways that have no classical picture at all. To even begin to picture how the inside of a black hole could be the same system as radiation that floated away eons ago and sits light-years distant, you need an idea that Maldaceno and Susskind put forward in 2013, an idea so compact it fits in an equation with 3 letters on each side. They wrote, ER equals EP-R. ER stands for Einstein-Rosen, as in an Einstein-Rosen bridge, which is the technical name for a wormhole, a tunnel through space-time connecting 2 distant places. EPA stands for Einstein-Podolsky-Rosen, the initials behind the most famous example of quantum entanglement, the spooky connection that links 2 particles so that measuring one instantly tells you about the other, no matter how far apart they are. For most of a century, these were treated as 2 completely unrelated pieces of physics, one from general relativity, one from quantum mechanics, living in different textbooks, taught by different people. Maldaceno and Susskind proposed that they are the same thing. That entanglement, the quantum connection between 2 particles, simply is a wormhole, a tiny, untraversable bridge of space-time stitching them together. That whenever 2 things are entangled, there is, in some real sense, a thread of geometry connecting them. Sit with what that does to the island. The deep interior of the black hole is entangled with the radiation that escaped, and if entanglement is a wormhole, then there is a geometric bridge connecting the inside of the black hole to that distant radiation, a tunnel that makes the faraway particles and the buried interior literally the same region, threaded together behind the scenes of space. The information was never trapped, because the inside was never as separate from the outside as it looked. Space itself, in this picture, is woven out of entanglement, sewn together thread by quantum connections, and a black hole is a place where some of those threads run somewhere you cannot follow. The reason the information gets out is that the geometry of space is made of the same stuff as the information, and you cannot wall information off using a fabric that is woven from it. I told you near the start that the answer to where does the information go would dissolve the meaning of the word where. This is the dissolution. The information is not in the radiation or in the interior, because, threaded together by entanglement that is also geometry, they are not fully separate places. The three-dimensional stage with its definite locations, the stage you have stood on your whole life, is starting to look like it is sewn together out of quantum threads, and the seams come apart exactly where a black hole is. A science writer named George Musser, writing in Quantum magazine in October of 2020, captured what the community was, cautiously, allowing itself to believe. Information, he wrote, does escape a black hole. Physicists were saying it now with confidence. If you jump into one, he wrote, you will not be gone for good. Particle by particle, the information needed to reconstitute your body will re-emerge. Read that again, slowly, because it is the most hopeful sentence in this entire story, and also, when you really look at it, the most horrifying. Particle by particle, the information needed to reconstitute your body will re-emerge. The information that was you. Not you. The information. Scrambled into thermal radiation, smeared across an expanding cloud of particles over a span of time longer than the current universe has existed, in a form so thoroughly shuffled that no conceivable process could ever reassemble it into anything resembling a person, a memory, a moment. The universe keeps the receipt. It does not, in any sense that could ever matter to you or to anyone, keep you. This is the part where the dread that has been rising under the whole story finally breaks the surface, and I have to be honest with you about something the headlines did not say. Because if you read the news in 2020, you saw the information paradox declared more or less solved, the universe vindicated as a keeper of records, quantum mechanics saved, a happy ending 45 years in the making. And the people who actually did the work will tell you a more careful thing if you ask them, and some of them said it in print. Netta Engelhardt, one of the architects of the island formula, has been clear that the resolution is a work in progress, that what was shown is that the entanglement entropy follows the page curve, which is a profound and real result, but that a full mechanism, an actual reverse algorithm that takes the radiation and reconstructs what fell in, does not exist and may never exist in any usable form. And almost all of this work was done in a special, idealized kind of space-time, the kind Maldacina's correspondence lives in, a universe with a particular curved boundary that is not the universe we actually inhabit. Whether it all carries over to a real expanding universe like ours is not known. The calculation that bent the page curve is a triumph. It is also a calculation done in a toy model, and the people who did it are the first to say so. I told you, back at Dublin, to watch for this, because the same thing was going to happen again with even better headlines, and it did exactly. In 2020, the story that reached the public was that the black hole information paradox had finally been solved, half a century after Hawking opened it. A clean, triumphant ending, quantum mechanics vindicated, roll credits. And that story is built on something real this time, more real than the Dublin concession ever was. A genuine and beautiful calculation that genuinely bends the curve the right way. But it is still the tellable version, still sanded smooth for carrying, still missing the part where the people who did the work raise their hands and say, wait, we showed the entropy behaves correctly. We did not show how. We did it in a universe shaped like a snow globe and not like ours, and we do not have, and may never have, the thing you would actually need to take a fistful of Hawking radiation and read out of it the person who fell in. The headline says solved. The footnote, written by the solvers themselves, says we are closer and we are not done. And the hardest part may be the part we cannot do. The pattern from 1974 repeats one more time at the very end of the story. The comfortable version travels. The honest version stays in the seminar room. And you, unless someone tells you otherwise, get handed the comfortable one and never learn there was a footnote at all. And even the optimistic version, the fully solved version that the most hopeful physicists believe is coming, does not give you back what you would actually want. And this is the thing I need you to be clear-eyed about. Suppose it all works. Suppose information escapes every black hole perfectly. Suppose unitarity holds in our universe exactly as it holds in the snow globe. Suppose the universe is proven, beyond all doubt, to keep a flawless and complete record of everything that ever fell into everything. You still do not come back. The record is not a resurrection. Preserving the information that specified a burned book is not the same as having the book, and you cannot read by the light of ashes. What survives, in the best case, the most optimistic case anyone is fighting for, is a perfect description of you, smeared across radiation, in a code with no key, in a universe that is busy removing every reader. The victory the physicists are reaching for is the victory of proving the universe does not forget. It was never the victory of proving the universe remembers in any way that could matter to the remembered. So here is the honest state of the question, the central question, the one we have been failing to answer for 2 hours, the one underneath the cup of tea and the bet and the firewall and the hologram. Does the universe keep a record of the past, or can it be erased? And the answer, as best we can currently give it, is this. The information is probably preserved. The smart money, after 50 years, is on the universe keeping its receipts. But preserved is the cruelest possible word for what actually happens to it, because preserved does not mean recoverable, and it does not mean readable, and it does not mean that anything, ever, could reconstruct from it the thing it used to be. The past is not erased. It is something worse than erased. It is converted into a form that is perfectly preserved and perfectly unreadable, scattered into thermal radiation over timescales that defeat language, kept in a vault whose combination has been thrown into the same furnace as everything else. The universe remembers everything and can tell you nothing, and it gets worse, because now we have to talk about how this ends, not how the black hole ends, how everything ends, because we established a long time ago that black holes evaporate, that the glow Bekenstein predicted and Hawking proved means these objects are slowly dying, and we have been treating that as the engine of the information paradox. But it is also, taken on its own, a statement about the far future of the universe, and the far future of the universe is the place where the second law of thermodynamics, the law that started all of this, the law Bekenstein refused to let a black hole break, finally collects its full and final payment. Let me give you the timescales, because the timescales are where the feeling lives, and you cannot feel a number you have not been made to hold. A black hole with the mass of our sun, left alone in a universe cold enough to let it radiate, would take about 10 to the 67th power years to fully evaporate. I am going to try to make that number mean something, but I want to warn you in advance that I do not think it can be done, that the number is past the edge of what a human mind can actually grasp, and that the failure to grasp it is itself part of the point. 10 to the 67th power years. The current age of the universe is about 14 billion years, which is 1.4 times 10 to the 10th power. So a sun-mass black hole lives roughly 10 to the 57th power times longer than the entire history of the universe so far. If you compressed the whole life of the cosmos to this moment, all 14 billion years of it, from the Big Bang through the formation of every galaxy and star and planet, and the entire history of life on Earth, and every person who has ever lived, down into a single second, then the evaporation of one ordinary black hole would still take a length of time so much longer than that second that the comparison is meaningless. The number does not fit. That is the honest report. The number does not fit inside a person. Let me try one more way to reach it, knowing I will fail, because the failing is instructive. Forget years. Imagine that once every 100 years, a single bird flies past the Earth and brushes the peak of the highest mountain with the tip of one wing, wearing the mountain down by the width of a single atom. The time it would take that bird, one pass per century, to wear an entire mountain range flat is laughably vanishingly short compared to the life of a black hole. You could grind every mountain on Earth to sea level that way, atom by atom, century by century, and then do it again for every mountain on every planet in the galaxy, and you would not have made a dent in the time a single sun-mass black hole takes to evaporate. Pile up every grain of sand on every beach on Earth and count 1 grain per year and you do not get close. There is no physical process at human scale slow enough to serve as a clock for this. The black hole outlasts every metaphor you can build for how long it lasts, and the supermassive ones outlast the small ones by another factor so large it makes 10 to the 67th look immediate. And that is a small black hole. The supermassive black holes, the ones at the centers of galaxies, millions or billions of times the sun's mass, take far longer, up to around 10 to the 100th power years, a number called a googol, a 1 followed by 100 zeros. These are the last things. After the stars have died, after the galaxies have gone dark, after every other structure in the universe has decayed, the black holes remain. The final monuments. The longest-lived objects reality will ever produce. And then, one by one, they too begin to evaporate, and they radiate, and they shrink, and as they shrink they heat up, because remember, smaller is hotter, and the heating accelerates, and the final moment of a black hole's life, after 10 to the 100th power years of patient glowing, is not a fade. It is a flash. A Yale astronomer named Priyamvada Natarajan described that final instant in a way I have not been able to stop thinking about. In the final 10th of a second of a black hole's life, she said, you get a huge flash of light and energy. It is almost like 1 million nuclear fusion bombs going off in a very tiny region of space. After 10 to the 100th power years of near-perfect darkness, the last black hole in the universe ends its existence with a burst that for a fraction of a second lights up its tiny corner of an otherwise empty cosmos like a star being born and dying in the same instant. And then it is gone. And then there are no black holes anywhere, and then there is nothing left in the universe that can do anything at all. This far future has a map drawn most carefully by 2 physicists, Fred Adams and Gregory Laughlin, in a paper published in 1997 in Reviews of Modern Physics, volume 69, titled, with a bluntness I appreciate, A Dying Universe. They divided the future into eras, and the names alone tell the story. We live in the stelliferous era, the era of stars, the era of light, and it is, on the cosmic scale, almost over, ending in something like 100 trillion years when the last stars burn out. Then comes the degenerate era, the long twilight of stellar corpses, white dwarfs and neutron stars cooling in the dark, lasting until perhaps 10 to the 39th power years, when even the protons that make up ordinary matter may decay, and the corpses themselves dissolve. Then the black hole era, from around 10 to the 40th power years out to 10 to the 100th power, when black holes are the only macroscopic objects left, the last things with any structure at all, slowly evaporating in a universe of almost perfect emptiness. And then, beyond 10 to the 100th power years, the Dark Era, a universe of dilute radiation and a thin scatter of stray particles, drifting ever farther apart in an ever-expanding void, approaching, asymptotically, forever, the state called heat death. Maximum entropy. The state where everything has reached the same temperature, where no heat flows because there is nowhere colder for it to flow to, where no structure can form and no process can run and nothing can ever happen again. I want to slow down on the loneliness of that middle stretch, the black hole era, because it is the part that does something strange to me whenever I think about it. Long before the end, in the degenerate era, the ordinary matter you are made of may simply come apart. The current best guess in many theories is that the proton, the particle at the heart of every atom in your body and every atom in every star, is not perfectly stable, that given enough time it decays, falling apart into lighter particles, with a half-life somewhere past 10 to the 34th power years. If that is true, then there is a time, unimaginably far off, after which there are no atoms left anywhere in the universe. Not broken atoms, no atoms. Every proton that ever existed, every one in every body of every creature that ever lived on any world, gone, dissolved into a thin drizzle of radiation. And after that, for a span of time that makes the entire age of stars look like a single spark, the only things left with any structure at all are the black holes, drifting in a cold and expanding dark, each one alone, separated from the next by distances so vast and growing so fast that they will never meet, never merge, never interact. Just hang there in the emptiness, slowly leaking their stored information back into a void that has no one left in it to receive the message. And then, one by one, across the long count of the black hole era, they flash and vanish, and the universe spends them like the last coins in a pocket, and when the last one goes there is nothing with structure anywhere, forever. The black holes are the universe's final memory, the last objects holding any record of anything, and the second law spends them too. This is where Bekenstein's cup of tea was always pointing. He started by refusing to let a black hole cheat the second law. He insisted the universe keeps its books, that entropy always goes up, that the crime is always recorded. And he was right, and the price of his being right is written across the far future of the cosmos, in numbers that do not fit in a human skull. The second law that he defended is the law that guarantees the heat death. Entropy always increases. It increases until it cannot increase anymore, and the state where it cannot increase anymore is a universe of perfectly even, perfectly useless, perfectly preserved disorder in which every receipt the universe ever kept still exists and not one of them can ever be read again, because reading requires a difference in temperature, a flow, a structure, a someone, and there is none of that left. There never will be again. So now I can tell you the thing this whole story has been circling, the implication that has been hiding under the cup of tea and the lonely years and the bet and the firewall and the hologram and the Google year flash, and I want to say it plainly, the way Bekenstein would have wanted it said, without softening it. Because softening it would be a lie. The information is preserved. The universe does keep a record of you, of everyone you love, of everything that has ever happened, scrambled into the radiation of evaporating black holes and the thin cold light of the dying cosmos, technically complete, technically recoverable in the way that the ashes of a burned encyclopedia technically still contain the book. And the universe is moving, with the full and irreversible force of the second law of thermodynamics, the most reliable law we know, toward a state in which that record exists and can never, by anything, ever be read. Not because the information was destroyed. Because the universe is becoming the kind of place where there is no longer anyone, and no longer any process, and no longer any difference between one part of reality and another, that could ever make the record mean something again. The past is kept. The past is also, finally and forever, lost, in a form that is mathematically indistinguishable from being kept. And the difference between those two things, between perfect preservation and total erasure, turns out to be the difference that the heat death erases last. Jacob Bekenstein did not live to see the page curve bend. He died on the 16th of August 2015 of a heart attack in Helsinki, where he had travelled to give a seminar. He was 68. He had, just months earlier, been awarded the Einstein Prize, one of the highest honours in physics, and 3 years before that the Wolf Prize, which is very often a precursor to the Nobel. Many people expected the Nobel would come. It did not come in time, and the Nobel Prize is not awarded posthumously, and so the man who first understood that black holes have entropy, the man who refused to let the universe forget, the man whose single insight launched 50 years of the deepest work in theoretical physics, and whose name is fused with Hawking's in the equation carved on Hawking's tomb, will never receive the prize that his idea, by any honest accounting, earned several times over. The universe kept the receipt for his work. The committee that hands out the medals did not, in time. He was, the people who knew him said, completely without bitterness about any of it. Modest to the end. Tenacious in defending his ideas and yet never a salesman for them. An Orthodox Jew who saw no conflict at all between the deepest reductionist physics and his faith, who wore a yarmulke to conferences where he was the most rigorous reductionist in the room, and who once said that he found in the order of physical law something that only deepened his sense of the sacred. He spent the lonely years being told he was wrong by the most famous physicist alive. And he was patient, and he was right, and he was generous enough when the vindication came to insist that the radiation be named after the man who had opposed him, because that man had done the part Bekenstein could not. I wrote it down first, he said. Hawking found the constant. So it should be called Hawking radiation. And there is an irony in Hawking's own life that belongs here, because this whole story has been built on ironic reversals, and his is the largest of them. Stephen Hawking was born on the 8th of January, 1942, and at the age of 21, in 1963, he was diagnosed with a motor neurone disease and told he had perhaps 2 years to live. He did not have 2 years. He had 55. He lived to be 76, building the deepest parts of this entire story from a wheelchair, eventually speaking only through a sensor that read the twitch of a muscle in his cheek, one word at a time, at a pace that would have driven most people to silence, and he used that excruciating channel to dictate the equations that taught the universe how black holes die. A man who had been handed his own evaporation date at 21 spent the rest of his life working out the evaporation of everything else. He, more than anyone, knew what it was to live as a pattern running on borrowed time, to be a configuration of matter that every prediction said should already have dispersed, and to keep holding together anyway, year after impossible year, doing the work. He spent his life studying the fate of the cosmos while outliving every forecast of his own fate. And when he died, on the 14th of March, 2018, which happens to be both Pi Day and the anniversary of Einstein's birth, his ashes were carried into Westminster Abbey and set between Isaac Newton and Charles Darwin, and the formula was carved on the stone above him. The entropy of a black hole, the thing he had tried for years to prove, was only a coincidence, the thing that turned out to be the truest thing he ever found. And Hawking, for his part, conceded everything that mattered. Bekenstein was basically correct, he wrote, in a manner he had certainly not expected. The skeptic and the student locked in the same equation, on the same stone. In the same cathedral, in the same 50-year war that neither of them lived to see the end of, because there is no end, because the question is still open, because we still cannot fully say, in the universe we actually live in, rather than the toy model where the math is clean, whether the past can be erased. But here is the last thing, and I am going to leave it with you exactly as heavy as it actually is, because you came here for the real version, and the real version does not get to end with comfort. You are information. That is not a metaphor, and it is not mysticism. The arrangement of atoms that makes you you, every memory, every fear, every face you can picture with your eyes closed, every word in this sentence as you understand it, all of it is a particular configuration of matter, a particular pattern, a particular set of receipts the universe is currently holding. And the same second law that Bekenstein defended, the same law that guarantees a black hole keeps its books, guarantees that your pattern is being slowly, inexorably erased into the background, smeared a little more toward equilibrium with every breath you take, every thought you have, every cup of tea you let go cold. You are, right now, in the very act of being alive, increasing the entropy of the universe. You are committing Wheeler's crime continuously with every heartbeat, and the universe is recording it, and it cannot be undone, and the recording will outlast the stars. The information that is you will survive the death of the sun, and the death of the galaxy, and the evaporation of every black hole scrambled into the cold thin light of a universe winding down. It will be preserved. Perfectly, permanently, in a form that nothing, anywhere for the rest of time will ever be able to read. The universe keeps everything. And then it makes sure no one can ever look